Hello and welcome to this video. In this video we're going to be looking at the heat transfer of a system and how we can quantify it and explain different ways that we can transfer heat. So the first law tells us that in order to change the internal energy of a system, we have to either heat it up or compress it or expand it or cool it down. Okay, now we're just going to focus on this heat transfer for now, and we'll do other videos where we look at the work done, since this will go into a little bit more detail on. But heat transfer can happen in two ways. Okay, the first way is by specific heat capacity. Okay, so the specific heat capacity is another property that we will have of each material. So water will have a certain specific heat capacity, aluminium will have a different one, iron will have a different one. Every different material will have its own value for specific heat capacity. And what the specific heat capacity describes is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. Okay, so it's the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. And for that reason, we can say that specific heat capacity is measured in joules per kilogram per Kelvin. Okay? And this means that any heat transfer that happens based on the specific heat capacity of the material, the whole point of this heat transfer is to raise the temperature, okay? Or reduce the temperature, just to change the temperature by 1 kilogram, by 1 Kelvin. Obviously, if you're going to input energy, you're going to raise the temperature. If you're going to take out energy, then you're going to decrease the temperature. But the whole point of this, regardless, is just to change the temperature of that object. And this, because of this quantity, we can then formulate an expression for the heat transfer in order to change the temperature. That's the mass, so we get rid of this kilogram, times by the specific heat capacity, which is this, times by the change in temperature that it actually goes through. Now, for the change in temperature, it doesn't matter too much whether you use Kelvin or Celsius, because the difference between the scale, for example, if I have a change of 1 degree Celsius, I also have a change of 1 Kelvin, right? There's no difference in the scale. So it means that actually you don't always have to convert to Kelvin when there's a change in temperature, although I would say it's good practice, but in general you don't really have to do it in this case. And so this then allows us to calculate how much energy we'd have to put in order to increase or decrease the energy by a certain amount. But this isn't the only type of heat transfer we can get. If we want to heat up the object, it means that we're going to raise the temperature. So heat and temperature are different things. Heat is an amount of energy, and temperature is the quantity that we define using the zeroth law. But if I want to keep adding in, if you've ever boiled water, for example, you know it doesn't just reach 100 degrees and then evaporate all instantaneously, right? There's still some time before you'd evaporate off a bunch of that water. So there has to be a second type of heat transfer to actually change states. And we call that the specific latent heat. So if anything is based off of the specific latent heat, the specific latent heat is defined as the amount of energy required to change the state of 1 kilogram of a substance. Okay, whether that's to change it from a liquid to a gas or a solid to a liquid will change the thing that we're looking at. Now, if we're looking at the amount of energy required per kilogram, then our units for the specific latent heat are just joules per kilogram. Now we have to then define a second equation to explain the difference between the specific heat capacity where we're trying to heat it up and the specific latent heat where we're changing its state. Now, what you would assume is that if I were to keep putting heat energy in, it doesn't matter what temperature it is, the temperature will continue to increase. But this is actually not true. We find that when we are boiling something to make it gas, or if we're starting to melt something to make it a liquid, there's actually an amount of time where it will continue to absorb energy, but actually won't ever change temperature. And this is why we can separate the two, because we have some energy transferred at a constant temperature. So this could also add on the end here that this is at a constant temperature. The temperature doesn't change while the state is changing, okay? And we'll look at a graph that's going to represent this in more detail. In order to get an equation, we would say the heat transfer during this time is the mass, to get rid of the kilograms, multiplied by the specific latent heat, which has this symbol L. Now, both of these formulas are on your equation sheet, and it is very important that you know the difference between them, and you know what the purpose of each of these things are. Now, the specific latent heat, like I said, there's two possibilities when we're changing the state of something. We can either be changing it from a solid to a liquid, or we can change it from a liquid to a gas. And then we have two separate definitions for those. So if we took the specific latent heat of fusion, this is to change from a solid to a liquid. And then if we were to take the specific latent heat of evaporation, you can already tell that this is going to take it from a liquid to a gas. Okay, so we have these two definitions, I guess, of the specific latent heat of fusion. We could alter this definition slightly and say it was the amount of energy required to change 1 kilogram of a substance from a solid to a liquid at a constant temperature, and then specific latent heat of evaporation would be the amount of energy required to change the state of 1 kilogram of a liquid to a gas at a constant temperature. Now, something that's kind of important about these is that the specific latent heat of fusion and evaporation will be different, okay? For the same substance, if I want to melt it to get it to be a gas, if I want to melt it to get it to be a liquid, I have to put in a different amount of energy to if I want to evaporate it to get it to be a gas. And actually that means that if the specific latent heat changes between phases, then surely that must mean that the specific heat capacity changed between phases. Because if I had to put in a different amount of energy to increase the energy of the whole, increase the total energy, so the state of the system, since we know that a liquid has more energy than a solid, if I have to put in energy or more energy now to get it to be from a liquid to a gas than I did from being a solid to a liquid, then surely that means that in order to change the temperature to get up to that point, my specific heat capacity also has to change in each phase. And this is true. We find that if I actually want to plot a graph of how the temperature changes with time, let me actually do a slightly larger graph. So I'm going to start, so this is my temperature, this is in Kelvin, and this is my time in arbitrary units. And I'm going to say, if I start at absolute zero, this thing is going to be a solid, okay? I'm making the assumption that it can be a solid. Not all metals or all materials can actually become solid at absolute zero, but for the most part, we can assume that a lot of them do become solid at absolute zero. And then I'm going to have some heat transfer that's going to go in, and I'm going to end up increasing the temperature of this to about here. Okay, now this state here is where the object is a solid. Then I reach this temperature, and at this temperature, this is the melting point of the solid, and hence I'm now going to put in more energy, so I keep heating at a continual rate for this whole thing. But now the energy is going to be used up at a constant temperature to change the state. So this is the latent heat of fusion that's being put in here. And then as soon as it reaches this point, it's now a liquid. And then from that liquid, it's then going to continue to rise. And at this point, it is a liquid until it reaches here, where it's going to be a constant temperature. And this is latent heat of evaporation. And then finally, we now have a gas, and now the gas temperature is going to increase. And so this is a general idea of how this changes. Now, this here would be the boiling point of this. And we can see that the amount of energy we've had to put in is a continual rate. Okay, so there is a continuous constant supply of energy. Okay, so there's let's call it Q for heat energy. So we're saying that if we just put this on an electric heater, for example, where we know for a fact it's always going to produce the same amount of heat for basically infinite time, right? We're going to assume we have a perfect electric heater. If we were to do that, we would find that we would still end up with this kind of changing temperature over time. But actually what's more interesting is the gradient of these things. Now, this graph doesn't show it to be specifically true, but what you can form from graphs like this is that the gradient at each point is proportional to the specific heat capacity. Now, obviously my graph is just a rough sketch, but we find that actually the specific heat capacity of in different phases is different, or different states is different, even for the same substance. Even if I take ice and I try to heat that up, I find the specific heat capacity of ice to be about 900 and something, and then if I take the specific heat capacity of water, it's about 4,200 and something. So I end up having a different specific heat capacity for different things, because it is now more difficult to increase the temperature of water because it can absorb more energy now before it increases temperature. So the things to take away from this video are that we can define a specific heat capacity, and we then formulate this formula, which then tells you how much energy you would have to put in order to increase the temperature of a substance by a certain amount. Then we have this defining the latent heat capacity as the amount of energy required to actually change the state of that substance while at a constant temperature. And we need to then be able to figure out that we can have latent heat of fusion, we can have latent heat of evaporation, and the specific heat capacity in different phases will always be different, even for the same substance. Now, a common thing that they will ask you to do is to actually add these two equations together. We can sum the amount of energy, so it is possible to get a total amount of energy transfer by saying that the total amount of energy, let's say we start with something, let's say we start with water, for example, at 10 degrees Celsius, and we then say we're going to boil it until it completely changes into gas. Now we have to say we need to first add in some amount of energy in order to actually heat it up so the temperature increases to the boiling point, which would be 100 degrees Celsius. And then we have to say we need to add all of the extra energy that we've put in to actually change the state of it. And so this is a common thing that they will do in exam questions, where they will actually tell you that you've heated it up by this amount and then you've changed the state of it. What's the total amount of energy that's transferred? And this is how you would do that. You can simply just add two energies together. Thank you for watching.